We're good?
Yeah.
All right. So thanks for coming, everyone. This is going to be a very different talk. Well, maybe a little bit similar. There's going to be some geometry involved, which is similar to some of the group theoretic stuff that's discussed. But this is a more statistical perspective. So I want to talk about tools for doing high-dimensional Bayesian inference, which is going to bring us to this idea of Hamiltonian Monte Carlo. And I'm going to spend a good bit of time motivating why we need tools like Hamiltonian Monte Carlo, why Bayesian inference is really hard, and why, in order to do it right, we're going to need tools like this that really exploit as much information about our problem as possible. So to motivate things, we'll talk a little bit about a kind of a conceptual example of the kind of problems that I'm interested in dealing with. Right? There's a zeitgeist of big data. Everyone talks about as much data as we're collecting, about 20 million labels, et cetera, et cetera. But the thing about data is that it doesn't fully specify the statistical problem. You don't care how much data you have. I don't know how hard your problem is going to be until I know the complexity of that data. What's the structure of that data? There's an infinite difference between IID data of the same subject versus heterogeneous data with complex time dependencies. And so the reality of doing data analysis is trying to identify where you live in this space. Are you the kind of scaling where you can collecting more and more data of simpler and simpler structures, what we call the so-called tall data regime? Or are you in the kind of circumstance where the more data you collect, the more systematic effects there are? Because you can't collect data of the same person over and over again. You're collecting data of different people in different circumstances, in different environments. This is the so-called wide data regime. And now in the middle, it's a little bit wishy-washy, but for all intents and purposes, for most intensive purposes, problems seem to demarcate into these two regimes. Now, there's a lot of fun machine learning we can all do in this tall data regime, and that can be a really good approximation to a lot of problems initially, right? If you don't use any kind of data at all, assuming a nice simple model is a good way of getting a good baseline inference. But when you start exploiting that data more, when you start trying to capture more and more of that structure, make finer and finer inferences, slowly but surely you are going to drift up into that wide data regime. And so inevitably we're going to have to tackle problems there. And in reality, problems in science and medicine, we're already there. We can't escape the wide data regime. So what I'm interested in is trying to build tools that facilitate analyses in this wide data regime, and particularly in the Bayesian paradigm. So in the Bayesian paradigm, we're going to take our data generating process that models all of that complexity. We're going to, of course, pair it with a prior distribution, which is extremely powerful in these circumstances where we don't have enough information in our data. Right? We have more complexity than information, and so the prior really allows us to incorporate principal domain expertise, drastically simplifying the problem and improving our inferences. Now we put these two things together with some data, we get a posterior distribution, and that posterior distribution captures all of the information in our system. It's this wonderfully kind of elegant theoretical property. But the reality is that we can't work with a posterior distribution. A high-dimensional probability distribution is a kind of meaningless thing. It's this abstraction that we can't interact with. In order to work with that distribution, in order to ask questions about the information encoded in that distribution, we need to take expectation values. Right? This is the fundamental operation in Bayesian inference. There's a modeling stage. We specify the prior and the likelihood. Then there's an expectation stage, a computation stage, where we compute these expectation values for various functions f. Right? It's in these expectations or various choices of f that we're able to interrogate this posterior, get useful information out of it. So if we kind of abstract this problem a little bit, once you specify a posterior, that's just a distribution. And the fundamental challenge of Bayesian inference is high-dimensional integration. Right? Bayesian inference is hard because integration is hard. That's it. And so once we distract that all away, we get a little more generality because there's lots of problems that reduce to integrals. Most of statistics, expectations. So kind of modulate that motivation, even if you're not super interested in Bayesian inference or high-dimensional statistics, at some point in your life, you're going to have to do an integral. And it's very unlikely it's going to be analytic. So how do we tackle this problem? Or probably more specifically, why is this hard? Well, this is going to be hard because in most cases, we don't have analytic results, which means we have to numerically approximate these integrals. And numerical approximation of integrals is pretty tricky because these spaces are big. Right? Just a kind of conceptual example. Let's put a grid down in a one-dimensional space. Right? What's the cost of that grid? If I do a quadrature over a grid with n points in it, it's going to cost n function evaluations. Right? Pretty simple. Now, if I go to a two-dimensional grid, that's going to be n squared. 3n cubed, 4n to the fourth. Right? In general, we get n to the d complexity of a naive grid search. And so in practice, with the finite computational resources that we have available to us, we're never going to be able to have a grid of any kind of density. Right? In 10 dimensions, if I want 10 grid points, it's 10 to the 10 function evaluations. That's not happening. So we have to be smarter about how we use our computational resources. In particular, we don't want to spend our computational resources on those regions of parameter space that don't contribute to these expectations. Where, in parameter space, would we not be getting a contribution to an integral like this? Interactive part of the talk? Sorry?
Trying to figure out where the low density subspaces are.
Sure. So, right. So it could be low density. In fact, it could be anywhere the integrand is 0. Right? If the integrand is 0, I get no contribution to this integral. So let's take that a bit further and exploit the fact that the integration is a linear operation. So if the integrand is big, at the same time, shouldn't the integral be bigger as well? So following that logic, don't we just want to go where the integrand is big and focus all of our computation in a neighborhood around that? Well, let's even go push this deeper, because most expectations that we consider, most functions f, are pretty uniform, at least relative to the kind of exponential tails that we see of most densities. So in that case, presuming that we have relatively simple functions, we can just go to a region of parameter space where the density dominates and focus all of our computation there. So why don't we just run an optimizer, get to the mode, and put all of our computation in some neighborhood around the mode? Sounds great, right? Completely wrong. Not how integration works. This gives you a terrible approximation to the integral. And the problem is we forgot something very, very important, which is the volume. Integration is not just evaluating a function. Integration is aggregating a function over some volume in parameter space. And the size of that volume matters. The more volume there is, the more function we get. So we have to take a more complex picture, so we have to start understanding how volume works, especially as we push into higher dimensional spaces. And spoiler alert, it's much more complicated than our naive intuitions would let us to believe. So let's consider a few examples that build up some intuition, even some rough intuition as to how volume behaves as we go into higher and higher dimensional spaces. So first simple example, one-dimensional line. I'm going to partition it with kind of constant lengths across the space. So I have a central length, and then I have two side lengths. The relative import of my central little area is about 1/3. Now let's go to 2 dimensions. I'm going to use the same side length. Now I have a box in the middle, but I have 8 boxes outside. Same change in each direction, only now I've got corners to contend with. So now the relative volume is only 1/9. If I go to 3 dimensions, it's even worse. There are 26 boxes around that central cube, or 23 cubes around that central cube. And so the relative importance is over 1/27. The more volume we have, the more corners we have, the more volume shows up away from our central little box. The more it looks like there's more things away from us, right? It's a more of a more. It's an acceleration. Same thing happens in a spherical picture. So let's imagine a spherical shell. In 1 dimension, our shell is just a line. So if I take a little radial distance in or radial distance out, same amount in, out. But let's go to 2 dimensions. If I go a little radial distance in, a little radial distance out, I get a wedge that's much bigger on the outside than the inside. 3 dimensions, the wedge is even bigger on the outside than the inside. Right? So the relative volume outside the sphere grows exponentially fast relative to the volume inside the sphere as we go to higher and higher dimensions. So volume in a high dimensional space is weird, right? It's always more stuff away from us, no matter where we are, right? I'm going to see more stuff away from me here. You're going to see more stuff away from you there. You're going to see more stuff away from you over there, right? It's just how volume works in these high dimensional spaces. So that means if we go back to our picture, yeah, there's a lot of density around the mode, but there's not that much volume. And so we have to take that volume into account. There's exponentially more volume as we move away from that mode. And the growth of the volume increases as we go to higher and higher dimensional spaces. So what matters when we're talking about what contributes to an integral is not the density, it's not the volume, it's their product. It's probability mass. And that looks something like this. Right? Probability mass is not going to concentrate at the mode. It's not going to concentrate in the tails. It's going to concentrate somewhere in between those two extremes. And so we kind of quantify this qualitative property with a kind of fuzzy surface that incorporates most of our probability mass. Right? It depends on a threshold you choose, but we get the sense that our probability mass is concentrating tighter and tighter in some surface that surrounds the mode. And we call that surface the typical set. This is where most of our probability mass is. This is where we get the dominant contributions to these expectation values. Now, the problem in reality is that the typical set is not going to be some nice simple sphere. It's going to be some complex surface. And as we go in higher and higher dimensional spaces, the surface is going to get thinner and thinner exponentially fast. So even once you're in 10 dimensions, this isn't some diffuse thing that you can go grab and grope for and find. This is a gossamer surface that's just lightly floating in space. You're not going to find this thing by accident. You have to find it with dedicated methods. And this is why integration is so hard. All of the things that we need to quantify in order to compute these expectations are hiding from us. And we need to find them in order to do this computationally accurately or with any kinds of computational efficiency. Now, one way of doing this efficiently is to appeal to something called Monte Carlo. In Monte Carlo, we draw samples from this distribution. And the thing about samples is that they have to follow probability mass. It's kind of the definition of what a sample is. But if all of our probability mass is in the typical set, then our samples will, in fact, concentrate in the typical set. So I can now approximate integrating over all of parameter space by integrating over the typical set. And now I can approximate integrating over the typical set by integrating over the samples that I've drawn. And so if I want to compute the expectation of some function f, I literally just average it over these samples. Right? You can kind of think about these samples as a stochastic quadrature grid, only one that dynamically adapts to the problem at hand. And we have these wonderful results that say no matter how many dimensions I have, these functions, these Monte Carlo estimators, will follow a normal distribution around the true expectation value. They're unbiased relative to the realizations of these samples. And the error, this is the really big thing, the error of the estimators can be quantified if we know the variance of the function and the number of samples that we've drawn. So we get this nice square root of n dependence in our overall Monte Carlo standard error that's independent of the dimensionality of the problem. And so this immediately solves a scaling problem, right? Right? So why wouldn't this solve the problem? Yeah, it's hard to draw samples, right? In order to know how to draw a sample, I need to know where the typical set is. They're the same problem. All I've done is recast the problem in a different manner, right? I haven't actually done anything useful. Well, I've almost done something useful, because there's a way of approximating exact samples that doesn't require the same kind of machinery. And that's using something called the Markov chain. So a Markov chain allows us to construct correlated samples from a distribution. And we're going to generate those with what's called a Markov transition. It's this operator t. And it tells me if I'm at a point q prime, what's the distribution of points that I can jump to. Right? If I sample from that distribution, it tells me where to jump. I do it again, and I just kind of start diffusing around space. That's not particularly useful. But if we can engineer a Markov transition to preserve our target distribution, or really just our target density, then something very magical happens. And importantly, this is a deterministic property. Right? You give me your deterministic density and a deterministic transition density. If I can verify this, no matter what kind of stochastic behavior I have, that stochastic behavior is going to behave in a very specific way. And the implication of that is that our transition operators, our transition densities, are going to concentrate towards these regions of high probability mass. No matter where we are, we're much more likely to jump towards the region of high mass than away from it. So we start in a big high-dimensional space. We don't have to know where things are. We just follow this transition operator. Right? We make these jumps, and we get a little bit closer. We go again, right? And we get the same kind of concentration towards the typical set. Now, we don't always jump towards the typical set. We just do so with exceedingly high probability. Now, if we repeat this over and over again, we eventually drift into the typical set. And once we're there, we're kind of confined, right? We can't jump away because everywhere else has so much lower probability mass. And if we keep running the Markov chain, it will eventually distribute across the entirety of the typical set. And when it's done that, it's given us the same information that we had with Monte Carlo. Now all we had to do, instead of drawing exact samples, was generate a Markov chain that had the right kind of invariance property. And that's much easier to do mathematically. All of that said, this isn't as great as it might sound, because the only guarantee we get from this is that our Markov chain Monte Carlo estimators, which now we're using the correlated samples from our Markov chain, this doesn't follow a central limit theorem. This only has an asymptotic guarantee. If I run that Markov chain infinitely long, I will recover the true expectation. But there is no guarantee on what happens for any finite n. And I need to remind you, infinity is a really big number. Okay? It is not something we're going to achieve in a practical amount of time. And this has real practical consequences. So to get a handle on why this is so important, let's first consider the ideal situation. Right? This is how everything behaves nice and properly. This is what you see in textbooks. It's not what you see in practice. So on the left, I have my cartoon of the typical set. I'm going to have a cartoon of a Markov chain that's behaving well. And on the right, I'm going to have a picture of the error of my Markov chain Monte Carlo estimator versus iteration. Right? So presumably, this will converge and get more accurate as we go. Now, initially, I have this convergence phase where my Markov chain finds the typical set. Those points are not helpful. They're not informative. They're not in the typical set. So they don't lead to any kind of accuracy in my estimator. And indeed, you see that we kind of maintain this large bias in the estimator for some long time. It's only once we find the typical set and make our first sojourn across it that we get this rapid transition where our estimator gets very good very fast. Once we've done that, and we start exploring again and again and refining our understanding of the typical set, we then fall into the square root of n convergence that we had in Monte Carlo. Now, incidentally, this kind of initial bias, the point that these initial states are non-informative, this is why you have things like burn-in or warm-up in Markov chain Monte Carlo. Right? You're throwing away those initial samples because they're not informative. At the same time, you don't need to throw away half your chain. It's probably like 10 or 100 iterations, or 10 or 100 effective samples worth of iterations that you need to throw away unless you're adapting. OK, so again, this is the nice idealized behavior. We have some initial convergence. And then we start exploring the typical set over and over again, filling in all our understanding, getting into this, or settling into this nice square root of n convergence of our estimator. But this need not always be the case. Indeed, what if I had a typical set that looked like this, that has this little pinch over here? This is a region of high curvature. There's a lot of really small length scales there. And a Markov transition typically has some kind of characteristic length scale to it. Right? We all have a kind of a characteristic gait we walk with. Right? It might be random a little bit, but it's pretty characteristic. Now, if I'm wearing big shoes or I have a big gait, the probability I'm going to fall into a small little crack is really tiny. Right? There could be a crack that goes down to the center of the Earth. If I'm wearing big shoes, I will never find that crack. I will keep walking past it over and over again. And the Markov chain is going to do the same thing. Our Markov chain cannot get into this region with any reasonable probability. And so it's just going to skip by it over and over again. So we're not going to get complete exploration of our typical set, which means we have to be getting biased estimators, right? We're not quantifying all of our probability mass. So we have a bias that somehow has to magically go away after an infinite number of iterations. That's kind of weird, but it does have a resolution. And it manifests, in order to the way the Markov chain gets around that seemingly contradiction, is a manifestation of a very weird behavior. Has anybody run kind of a Gibbs sampler on a hierarchical model before? OK. I'm going to come back to you all. So we have our kind of, on the left, our cartoon of the typical set, only now we have our pathological neighborhood. I'm going to show the trace plot of the vertical direction in the central plot. And then on the right, I'm going to show the error of the estimator again. Except this time, I'm not going to have an absolute value. It's just going to be absolute valued. Right? So it's going to be a signed error. Now, what's going to happen? OK, so now we run our Markov chain. Let's assume we found it. Right? There's no convergence that we have to worry about. We're already in the typical set. And we start exploring. And initially, our Markov chain is fine. We're jumping around this nice, well-defined corner over here. Our trace plot looks great. And we're getting the kind of nice square root of n convergence that we'd expect. And then all of a sudden, our chain freezes. Right? Seen this before? Yeah? This means your Markov chain's broken. Right? Your Markov chain cannot get into that region. And so what it's trying to do is compensate by being really stubborn and just squeezing up against it as much as possible, right? It can't get through the door, so it just does this over and over again. Now, as stupid as that sounds, it does kind of correct our estimator a little bit. And our bias flips and goes to the wrong side. So it's a correction. It's a very, very crude correction. Now, if we keep running the Markov chain longer, it eventually decouples. It gets unstuck and starts exploring the good regions again. And you can see our estimator error comes back up. So the way the Markov chain resolves these two seemingly contradictory behaviors is through this oscillatory convergence. There's kind of a very large bias most of the time. There's these very short periods. I drew this a little bit biasedly so you could see it. But in practice, these periods of freezing are very, very short. Right? So you get this kind of period of very large bias. All of a sudden, there's a period of very large negative bias. And then it equilibrates back up to having large bias again, large positive bias. And that repeats over and over again. And in the infinite limit, that all cancels out. And we get 0. But it is a very delicate cancellation. And if you cut it off anywhere, you throw it off, and you get your bias again. Right? And so this is not the kind of fragile behavior we can utilize in any kind of robust way if we want to estimate these expectations accurately. We want that first ideal circumstance. We do not want things like this. Now, what we'd really like to have is a Markov chain Monte Carlo central limit theorem. Right? We like to have some kind of thing that guarantees that we have this nice unbiasedness for finite n, which requires additional conditions. Right? That invariance that you typically see in textbooks is not enough for practical utility of Markov chain Monte Carlo. We need additional considerations on the interaction of our Markov chain with the target distribution. Those have to play nicely with each other. And if we have these higher order properties, then we get something called geometric ergodicity, which guarantees a central limit theorem. Only now the number of samples n has been replaced by the effective sample size, which takes into account autocorrelations for a given function. Right? And again, this requires very careful kind of pairings between our target distribution, pi, and the transition operator t. Some transition operators might be geometrically ergodic with respect to some target distributions, and then not with respect to others. Some target distributions might be just very pathological and prevent most transition operators from being geometrically ergodic. And as we go in higher and higher dimensions, this kind of pairing gets harder and harder and harder. Now, we can start looking look at this cartoon of a typical set of a high-dimensional space behavior to get a feeling of why this is going to get harder as we go into higher and higher dimensions. Right? Why these two things start diverging unless we can incorporate additional information. And so to do that, let's look at Random Walk Metropolis. Right? Literally the first Markov chain Monte Carlo algorithm, and still today one of the most used. Probably because you can write it in 3 lines of R code. Does not mean it's a good idea to use. So Random Walk Metropolis proceeds in 2 stages. There is a proposal step, where we typically just add some Gaussian noise. Right? So I start at some point q prime, and I add some Gaussian noise to determine where I'm going to jump to. Then I'm going to correct, or I'm going to accept or reject that point based on the density. If I jump to a region of higher density according to my target, I accept. If I jump to a region of lower density according to my target, I reject. Now, what do these 2 steps do? The first step preferentially selects out regions of parameter space that have high volume. Right? If I take 2 neighborhoods, one has more volume than another, I'm more likely to jump in the region of high volume than low volume. But this acceptance procedure only selects jumps that also go to regions of high density. So the only thing that survives this process are neighborhoods of parameter space that have high volume and high density, which is, of course, the typical set. Right? So there's a tension going on. These 2 things are trying to do different things. And that tension is going to grow as we go to higher dimensional spaces, which is a manifestation of the problem that we're getting kind of a worse and worse pairing between our target density and our transition density. Right? So here's a cartoon. Nice cartoon of that. So take our point in green there. We're in the typical set. Now we want to explore it. If I make this Markov proposal, or this Metropolis proposal, it's nice and Gaussian, what is it going to look like in this kind of cartoon? Is it going to look nice and spherical? Not quite. So where is there more volume? Outside this typical set or inside the typical set? I hear a lot of mumbles. There we go. Thank you. Outside the typical set, right? So our intuition of isotropic isn't going to quite work. That vision of isotropic gets warped by these high-dimensional spaces, right? So we get more of a spade, because most of these points end up falling outside the typical set than inside. Now, if I make a big jump, all of my points are going to fall far outside the typical set, but that's going to be falling away from the mode. That's where the density gets really small. And so all of those jumps are going to get rejected, and I have to go back to where I started. I don't move at all. On the other hand, if I shrink the size of that transition, I still move away from the mode with high probability, but I don't move so far away that I leave the typical set. So these get accepted. But I have to shrink the size of that transition so much that I'm just diffusing in this infinitesimally small little neighborhood around where I started. It turns out no matter how you tune Random Walk Metropolis, the optimal tuning, the performance of the optimal tuning rapidly decreases as you go into higher and higher dimensions. Right? Because no matter how you tune this algorithm, you're never going to have this transition match the structure of the target distribution. And so if we want to scale something up a higher dimensions, we need to be able to exploit the structure of the typical set itself. We can't ignore it. We can't guess and check. Right? We can't waste that computation, because there are so many ways to fail that guess. In order to do better, we need some more information to guide us along this typical set. Right? We need something that tells us how to surf through these regions of high probability mass to very rapidly move away from where we started to get to new unexplored regions of the typical set. And to do that, I'm going to use a vector field. Well, sorry. So this is how we get to Hamiltonian Monte Carlo. Hamiltonian Monte Carlo is the unique procedure for generically constructing these kinds of trajectories that move through the typical set of continuous probability distributions, or really smooth probability distributions. Now, there's a lot of beautiful math involved with this, a lot of wonderful differential geometry that I will not force upon you. I'm going to instead use cartoons to build up some intuition as to what's going on. All right, so we have our typical set, and I want to inform how to move through this. How do I follow these nice trajectories? And again, I can't guess and check. I need something to tell me where to go. And a very natural way of doing that is with a vector field. So if I have a vector field that's particularly aligned with the typical set, then I don't have to guess where to go. I just look down and I see an arrow. And I can just blindly follow the arrow and find a new arrow and follow that. I don't need to know anything about the global structure of the problem. I just follow these local arrows, integrating along the vector field and generating the trajectory I want. Now, this may not seem like we've done anything better. We've turned the problem from these trajectories we can't construct to a vector field we can't construct. But this vector field is actually a little bit closer to reality, because I know how to construct a vector field that incorporates information about the target density. Right? So if I specify my problem with the target density, which of course is largest at the mode and then decreases as we move away from the mode, and we have the cartoon of the typical set around it, the gradient of this density is a vector field. Right? And that vector field clearly incorporates some kind of corresponding geometry that's capturing some structure of the typical set. It's just not quite the right geometry. Because if we flow along the gradient, we don't stay in the typical set. We fall away from the typical set and crash into the mode. What's missing here is some sense of volume. Right? This is just density. It can't stay in the typical set. So if I have some kind of volume that tells me how to take a complement of something, how to take something orthogonal in some sense, right? That requires a global sense of volume. That would allow me to twist the gradient to point along the typical set. Right? Literally just take these arrows and take a complement to them. And that points out the thing we want. Now, the procedure of doing that, of introducing some kind of geometry about the volume of the system, is Hamiltonian Monte Carlo. It uses this wonderful symplectic geometry to make that correction. But the really exciting thing, at least for this talk, is I don't have to explain any of that, because that math also happens to be the math that describes classical physics. So instead of trying to reason about this in a purely mathematical perspective, I can think about a physical perspective. Right? So let's ignore the mode, the gradient, and the typical set, and instead think about a planet, a gravitational field, in an orbit. Mathematically, this is the same exact system. Now, they're the same system, so they suffer from the same pathologies. And if you take a satellite and let it free fall in gravity, what happens? No, free fall in gravity. Just drop it. Towards? Boom, right? It's the same problem, right? It's following the gradient field and crashing into the planet. But how do we fix that? We're pretty good about putting shit in space. Probably too much stuff in space, right? But how do we keep things in orbit? Yeah, we need a push, right? We need some inertia to fight against gravity. We got to be careful in how we do that. If I add too little inertia to the system, well, I still crash into the planet, right? I delay the inevitable by a little bit, but I still eventually fall in. On the other hand, if I add too much momentum, well, then gravity's not strong enough to capture my little satellite at all, and it flies off to infinity. But if I had just the right amount of momentum in just the right direction, well, then the equations of motion that describe my evolution, they're exactly the vector field I want. And indeed, the physical evolution of that satellite traces out the trajectories that I want. So if we take this physical picture and map it back through the mathematical equivalence, the key to taking that gradient of our density and somehow correcting it to get the flow that we want is to add these momenta-like parameters, and to do that in a very careful way. And that is exactly what Hamiltonian Monte Carlo is. It's a way of adding auxiliary parameters to correct the gradient, to point in the directions that we want. So I'm going to go into just a bit more detail about how this works. So I'm going to take each one of my parameters Q and add a corresponding momenta P. I'm going to double the size of my space. Call this phase space. And at the same time, I'm going to take my original target distribution, I'm going to lift it to a distribution over phase space. So I need to add some probabilistic structure to the momenta as well. And I'm going to do that by specifying a conditional for P. And the reason I do this is because I can integrate out the momenta, and I'll always recover my original target distribution. So I'm going to lift up to this larger space, but at any given time, I can always stop, throw the momenta away, and I'm going to recover the thing I care about. Now, this joint density over here has a very special property in that its product is actually coordinate invariant. Its product is no longer a density because of the way we add these momenta. And in fact, the minus log of that product, something called the Hamiltonian, quantifies all the information we care about in the typical set. Now, this Hamiltonian, you can see it's a log of a product. So I can split it up into two terms. And the first term here, the minus log of the conditional density for the momenta, we call it kinetic energy. This is using the physics analogy a little bit too hard. The other term, the minus log of the target density, is a potential energy. Now, what's important here is that the potential energy is specified by our problem. The kinetic energy is not. Any choice of kinetic energy, any choice of conditional distribution for the momenta yields a Hamiltonian Monte Carlo algorithm. Hamiltonian Monte Carlo is not an algorithm. Hamiltonian Monte Carlo is a class of algorithms that follow this construction, and there are many, many ways of specifying a particular implementation. First and foremost is this choice of kinetic energy. Now, once we have chosen this Hamiltonian, in other words, once we've chosen this kinetic energy and potential energy, we get a vector field, something called Hamilton's equations, that point in this higher dimensional phase space. So you can see we have an arrow that points in the position direction. We also have an arrow that points in the momenta direction. What's important about these equations, particularly this latter one, is the presence of dVdq. Remember, V was our target density. dVdq is the gradient, right? It's that gradient we were talking about before. What Hamiltonian Monte Carlo does is it doesn't apply the gradients directly to the positions. It's not a gradient flow. It applies the gradients to the momenta, and then it's the momenta that shears the positions around. It's this indirect application of the gradient that gives it the twist that gives us the motion that we want. Right? And the mathematics ensures that no matter what the choice of k is, that twist is always perfect. so that we get the exact acceleration to the typical set. So the cartoon of this looks something like this. We have our typical set here, and we start at a point in it. And the first thing we're going to do is going to lift up onto phase space by sampling some momenta. So we're going to sample from our conditional density that we've specified. And what that means is that if I start in the typical set of pi of q, then I will lift up into the typical set of pi of pq. Once I'm there, I can follow Hamilton's equations for some amount of time, in fact, a random amount of time, if I really want to maximize my statistical performance. And then I integrate, so I choose a time randomly, I integrate for that amount of time, and what's the magic here is because we chose our joint density to be a conditional of p given q and then q, at any time, if we throw the momenta away, we fall back into the typical set of our target. So what this means is these trajectories that we've constructed, they cast a shadow that moves through the typical set. And it's the shadow that's actually giving us the acceleration that we want. All right, so at the end, we project back down. We get a point q prime that's in the typical set, but very, very far away from where we started. Much, much more efficient use of our precious computation than trying to diffuse all the way over there. So in practice, it looks something like this. So the thing I didn't mention is that we have to numerically integrate these trajectories. We have to use these symplectic integrators that are super powerful and super accurate and amazing. And if you ignore them, everything falls apart. So any kind of paper that ever claims to do Hamiltonian Monte Carlo without a symplectic integrator, just walk away. But when we use those symplectic integrators, we get these wonderful algorithms that look something like this. Right? So I start at some point. I build this trajectory dynamically. This is actually a feature of the Hamiltonian Monte Carlo we use in Stan. And then when we're done, I'm going to stop, and I'm going to sample a new point from that trajectory. And then I just keep going. I just build these trajectories that span the parameter space, fill up the typical set, and then I just pick some point that randomly fills in, kind of optimally explores the regions of high probability mass. Right? And then I do this over and over again and very rapidly build up a Markov chain that takes advantage of the computation that I have. Now, the power of Hamiltonian Monte Carlo is really threefold. So here I've talked about how it's super fast, right? But what really matters is when is Hamiltonian Monte Carlo geometrically ergodic? When do we get a central limit theorem? And we can show theoretically that indeed Hamiltonian Monte Carlo is geometrically ergodic with respect to lots of distributions. It's very robust. It's hard to break. But it's not that hard to break, right? It's harder to break than most other algorithms. The really cool thing about Hamiltonian Monte Carlo is that when it breaks so spectacularly that we can capture it and report it to the user. Unlike most algorithms, Hamiltonian Monte Carlo has unique diagnostics for when it's broken. So it's this perfect trifecta, right? When it works, it's really fast. It works for a lot of problems. And when it doesn't work, it tells us. That makes it a really powerful choice for automating Bayesian computation. And that's why it's the tool of choice in Stan. So Stan is a platform for Bayesian inference that tries to abstract away computation as much as possible so users can focus on building complex models. So we have a modeling language. This is one of these fancy probabilistic programming languages everyone throws around, except ours is really good. And it's used for specifying these complex, bespoke, principled Bayesian models. Once we have that model, it specifies a posterior density. We can use automatic differentiation to pull out the gradients automatically. So we have a state-of-the-art C++ automatic differentiation library. And then once we have those gradients, we can run Hamiltonian Monte Carlo, automatically adapt it, and check diagnostics. So all the work I do is exploiting the differential geometry behind all of this to understand how do we automatically adapt it, how do we optimally implement this algorithm, and then how do we diagnose whether or not we're getting accurate computation. Right? So by automating these two steps as much as possible, the users can focus on building these really spectacular models, which makes Stan a go-to tool in fields as diverse as pharmacometrics and physics and psychology, computational linguistics, ecology, et cetera. Right? It's a very generic tool with lots of very powerful, exciting applications. Now, all that said, Hamiltonian Monte Carlo is great, Stan is great, but there's still so much more that's coming down the track. First and foremost, bimodal problems. If I have a problem that has multiple modes, HMC is not going to fix it. HMC is great. It's not that powerful. Multiple modes, trying to calculate marginal likelihoods, that stuff requires more global information than gradient can tell you. But it turns out we can actually generalize Hamiltonian Monte Carlo to something called Adiabatic Monte Carlo. Adiabatic Monte Carlo moves along contact geometry trajectories instead of Hamiltonian or symplectic geometry trajectories. And so what that means is I get these dynamic trajectories that move not just through position and momentum space, they also move through temperature space. This is going to temper for me automatically. So I kind of start at some simple distribution. I run these dynamic trajectories. This is completely deterministic. And those trajectories are going to evolve, follow the changing distribution, and eventually settle into the modes. And if I run this over and over again, I fill up the modes with the exact probabilities that I should. Right? This tells me how to exploit more global information with the gradients to get at these much harder problems. Now, this is still for sampling, right? It's just for sampling more complex problems. I don't care that much about optimization, but I know a lot of people do. So let's go ahead and fix that too. So Nesterov accelerated methods, very powerful, very kind of confusing. Why do they work so well? Well, Winnaboso et al. Showed a few years ago that there was a dynamical system behind a lot of this stuff. And if you discretize it in just the right way, then you could get these Nesterov algorithms, like the exact discrete updates. Well, but they had to do this very weird heuristic discretization to stabilize those dynamics to get the results that they wanted. But if you have a dynamical system, there's a Hamiltonian involved. You want to use the symplectic integrators that we use in HMC. And so if you take those systems, you correct them in just a very careful way, you can apply the symplectic integrators. And what you can show is that you can get the same kind of qualitative performance as Nesterov, but you can show that Nesterov is actually doing two things. Nesterov is doing these kind of dynamics, and then it does this gradient flow at the end to get this kind of exponential behavior, this kind of shoulder right here. Right? So we can use the same geometry that we use for sampling to get a better understanding of what's going on in these optimization problems and get a better discretization so we can better implement them going forwards in the future. So a lot of really exciting work here being done with Mike Jordan and Aisha Wilson. So that gives a kind of a broad view of some of these applications, and it's just a really powerful tool. Right? If you kind of think about it, a typical set is a surface for all intents and purposes. Right? That fuzziness can be largely ignored. And if we want to exploit information about a surface, that's geometric information. Right? So it's not surprising that Hamiltonian Monte Carlo, which is built on this geometry, is a natural choice for these high-dimensional spaces. Right? Because it's exploiting the information in the right way, speaking the right language of these high-dimensional distributions. Right? That's why it's so powerful. That's why it's really pointing out the next level of algorithms in all of these very disparate fields. So I'll just end very quickly, also noting that I am a consultant. So if you want to play with Hamiltonian Monte Carlo or learn about it, or use Stan, or learn Bayesian Inference, I'm also available to help. I do courses. I teach all this kind of stuff at a much more deeper level, both on the theory and the applied side. Otherwise, I'll leave it at that. Thanks.
Thanks for the great talk. One of the things that I had to look at Stan, but I wasn't able to use it for one of the problems I had at hand because of the need of this meta language, as the fact that you cannot just use any arbitrary unnormalized posterior. Is there anything you can do when the gradient is hard to compute?
No. Right.
Good. So, or when you just have an unnormalized posterior implemented in a given language that for a given set of parameters gives you a number.
No. So the main thrust of the theory in all of this is that the gradients are critical. The gradients are what generate these flows. It's the gradients that gives us the exploration that we're after. Now, if it's just a problem of not being able to compute the gradients, we actually do a lot of that in Stan. If you have an ODE system, we'll compute the gradients. If you have a fixed point solution, we'll compute the gradients. Right, so a lot of these systems that are just natural obstructions actually quite naturally emit gradients if you're careful with the analytic structure. And that's something we're working a lot on in Stan to expand the language to have a lot of those features so things can be ported in a natural way. That said, there are still structures that don't have gradients. Right? Discrete problems don't have gradients. Now, some discrete problems, things like 0-1 hot encodings or even a 1 of k encoding, right, that can be marginalized out. It's a process called Rao-Blackwellization. And instead we use the probabilities. Those probabilities fit amazingly well in Stan. In fact, statistically, they should fit better because it's a summary statistic, the variance is lower, et cetera, et cetera. So problems like that can be handled by marginalizing things analytically, which leaves really complex, it's things like networks and trees, phylogenies, and just general networks that Stan can't really handle. And I would argue we don't know how to fit those in general. You know, you can run a random walk chain on a graph space. You can run a random walk chain on a tree space. I don't think any of the algorithms out there are really giving us a good, accurate sense of uncertainty. And those problems are not exploring the typical set of those spaces. And so that's a very important future step in research. A lot of interesting little things here and there that are starting, but nothing yet that I think has come close to really giving us a practical tool. High-dimensional spaces are hard. They hate you. They don't care about you, right? And gradients are your only weapon, right? It's dangerous to go alone. Take this. It's a gradient field.
Has there been any progress in inference in large data sets where you want to split up the data on multiple distributed nodes?
Right. So I would say no, in contrast to many people. So going back to this cartoon, right, this kind of tall data, large data regime thing, every method that tries to split up the data sets, right, lives down here. Anytime you can separate out your model and then just kind of aggregate it, you have to have this tall data structure. It doesn't work when you have complex correlations. But if you're already in this regime, you can throw a lot of data out because it's redundant, right? It's the redundancy that allows you to bring things back together. And so you might be able to get a little bit further pushing into the wide data regime, but not enough in my opinion.
Wasn't there this work on stochastic Monte Carlo a couple of years ago?
Oh, yeah, there's all kinds of approaches, right? There's approaches where you kind of literally split up things into Gaussians and multiply them together. There's approaches where you use stochastic gradients, which also fail pretty spectacularly. And so, you know, these problems are hard. You need all that information. That's the whole point, right? It's the same issue. It's not only do you need the gradient, you need every little bit of information in that gradient. And so I'm a modeler, right? I'm a scientist by training. When I have these problems with big data, if it's not IID data, it means there's structure that needs to be modeled. So what I'll do is instead take an iterative approach. I'm going to start simple. I'm going to take a small data set, a relatively small data set with a relatively simple model, and I'm going to expand it. And so I'll add more and more data as I can, and at some point I'm going to notice there's heterogeneity and time dependence and other systematics. I then model that, and I go as far as I can. So instead of trying to have some kind of algorithm that's biased, but I can't quantify the bias, I'm going to take an algorithm that has larger variance, but I can quantify the variance. That's how I approach these things. And it tends to work very well in practice, but it, of course, doesn't solve all the problems.
Yeah, nice talk. Thanks very much. You motivated HMC earlier with this sort of interesting heart-shaped density. And you said that your MCMC sampler will break at the kink. Well, it doesn't break, but it does a weird sort of stalling at the kink.
Yeah.
And then you said that HMC kind of works for these smooth probability distributions. So how does the kink and the necessity of needing a smooth distribution kind of fit together?
Right. So so that kink was a little I kind of drew it a little bit exaggerated, right? Right. It's not an actual kink here. It is smooth if you write it out. This is just a hierarchical model. So when you look at the log of the population standard deviation over any of the random effects, you get this kind of funnel shape. And it manifests in a typical set that kind of looks like a bike seat. And it is a little rounded, so I went a little bit, crazy here.
Slightly antagonistic question. Mm-hmm. Does it really matter that we don't quite capture the tiny kinks if they're tiny?
So that's up to your choice as a modeler, right? There are applications where you don't necessarily need that. But as you go to higher and higher dimensions, this actually bias gets quite large, right? So, for me, I'm absolutely fine if we take a principled stand where we know there's some bias and we can quantify it. We want to move on past that. My problem is that when we can't quantify that bias, and that's the problem by running, say, a Gibbs sampler on this or Random Walk Metropolis, is that there's a bias there and it's really hard to figure out. You might not even know that it's there, right? People run with these trace plots where it freezes. They report that in papers all the time. And to be totally the truth, HMC does not fix this problem, right? HMC gets a little bit deeper, and to be totally honest about things, right? These too many animations ruin this last part, right? These trace plots actually come from HMC, right? The same problems happen with Gibbs and Random Walk Metropolis, but it's so much longer. Like these iterations go in the millions instead of the tens, right? So I just did HMC to make it a little bit quicker. So HMC does do a little bit better, but the important part is it has these diagnostics. It diverges when it finds these things, and so it's very easy to tell. You don't have to wait to try to see your trace plot freeze. You know immediately. And then you go to what's called the non-standard parameterization. Everything gets magically fixed. And then conditioned on choosing those two parameterizations, HMC is orders of magnitude faster in both of those circumstances anyways. Right? So it's faster, it's more robust, but it's really the diagnostics, if anything, that make it more powerful. That's just an example of why MCMC can be kind of bad. Any other questions?
If I understood correctly, when you want to do the inference, you need a Hamiltonian, and that is specific to the problem that you are facing. How you build the Hamiltonian for a specific problem?
So the Hamiltonian is two components, right? Let me pull up the equation. So the Hamiltonian has a contribution from the target density and from this kinetic energy, right? So the kinetic energy is a choice. That's something we have to specify. One choice of kinetic energy gives us Euclidean Hamiltonian Monte Carlo, which is the tool in Stan. One choice of kinetic energy gives us Riemannian Hamiltonian Monte Carlo, which you may have seen in some papers. But we're going to choose that. That's going to be a tuning parameter for the implementation. The target density is given by the user. That's the problem that we're trying to solve. So one input is completely specified by the problem given, and one input is a tuning parameter that we have to use to specify which kind of HMC that we're actively using. And so there is a lot of work that we need to do to make sure that the choice of kinetic energy is paired well with that target density. And that leads, there's other diagnostics that I get into. There's an energy fraction of missing information. There's more geometry we can use to understand this interaction. That's why we have dynamical integration times. That's why we have dynamical step sizes. That's why we have these other diagnostics at hand I just unfortunately didn't have time to talk about. But there is a lot of theory as to how we do that. Any other questions? Can you use the mic?
Does it look like entropy, or is it just something I imagined up? This is nothing to do with entropy, or
Yeah, so the question is, does this look like entropy? No, this is not entropy. Entropy is interesting, right? So entropy, as people write as P log P, that is not a probabilistic quantity, right? Log P is a density-specific term. And entropy, the only well-posed entropies in probability are KL divergences, are relative entropies. Except on these symplectic manifolds, these phase spaces that we have, it turns out there's a canonical uniform measure. And so there's a canonical entropy, right? So if I take, the canonical entropy is the integral of e to the minus h times log of e to the minus h, which is just e to the minus h times h, right? That's the entropy on this kind of canonical entropy on these spaces. That's why in physics there's an entropy, but there shouldn't be an entropy in statistics or machine learning. It's either KL divergence, that's the only thing that exists there. So if you're on one of these spaces, you can talk about entropy. Otherwise, it's kind of misleading. Interesting little fact there. But yeah, so you can. And there are a lot of statistical mechanics takes advantage of that. In HMC, we haven't done too much, although you could argue that some of the diagnostics can be kind of rewritten and changed into that form. So a lot of the theory does as well. So a lot of proofs that we do kind of take that form implicitly. Joey? Yeah.
Let's thank the speakers again.